This is problem 105 from chapter 17. If the coefficient of static friction between the 50-pound roller and the ground is 0.25, determine the maximum force P that can be applied to the handle so that the roller rolls on the ground without slipping. Also find the angular acceleration of the roller. Assume the roller to be a uniform cylinder. So a uniform cylinder means a uniform density, a uniform mass density for the cylinder. And if the cylinder has a uniform mass density, then we can look up the moment of inertia for the cylinder in the back of the textbook for an axis going through the mass center. We get, that's the z-axis here, so that's 1/2 mr squared. And I'm going to do this problem symbolically and then put the numbers in at the end. Whoops, 1/2 r squared. So I'm going to say the radius of the cylinder is r and the mass is m. And then not only can I find the numerical answer for this problem, I can also look at some other questions when I have found the symbolic expression for Pmax. Okay, so I need to draw a free body diagram for the cylinder. So I have the force of gravity acting downwards at the mass center. I have this force Pmax. Let's just call it P. And it's acting at an angle of theta from the horizontal. And if the cylinder is going to roll instead of slip, I must have a force of static friction acting to the left, which will cause the cylinder to roll like this as it accelerates this way. And because we're looking for the maximum force P here, the static frictional force is at its max, and then we have the normal force acting upwards. I can sum up the forces in the y direction, I can sum up the forces in the x direction, and I can sum up the moments, and I'm going to do that about point G. When I sum up the forces in the y direction, there is no acceleration in the y direction. So the sum of the forces in the y direction is equal to 0. I have a sine component of this force P, which is acting downward. Since the acceleration in the y direction is equal to 0, I can say the sum of the forces, the sum of the upward forces is equal to the sum of the downward forces. So I have P sine theta plus mg is equal to the normal force. Then for the sum of the forces in the x direction, that's the mass times the acceleration in the x direction. And in the x direction, I have P cosine theta acting to the right. I have the maximum value for the force of static friction acting to the left. That's equal to the mass times the acceleration in the x direction. Now, if I sum up the moments about point G, that's equal to the moment of inertia about G times the angular acceleration. The moment of inertia is 1/2 mr squared, so that's 1/2 mr squared times the angular acceleration. For the sum of the moments about point G, since force P and the force of gravity are being applied right at this point, you get 0 for those two forces. And for the moment, you do the vector r, which goes from G, in this case, to where your force is being applied, and you do the cross product of r with the force. So for n, you'd get 0 since the vector r, which goes from the point about which you're summing up your moments to where the force is being applied, is at an angle of 180 degrees to the normal force there. So you get 0 for the cross product. So then you just get r times the maximum value for the force of static friction for the sum of the moments. Now when you do the cross product here, it's r crossed with your vector, so that's like this. That's in the negative direction, but I'm just going to say we're summing up the moments in the clockwise direction here, and then the angular acceleration is also going to be in the clockwise direction, so we're just going to call the clockwise direction positive. Because we're looking for Pmax so that the cylinder is rolling without slipping, we can say for rolling without slipping, The acceleration in the x direction is equal to r, the radius, times the angular acceleration. If the angular acceleration in the x direction is this way, if the acceleration in the x direction is this way, your angular acceleration is going to be like this in the negative direction, except that we called that the positive direction when we summed up the moments. So we can say this, and we can put that in here for the sum of the forces in the x direction. Let's call this equation 1 for the sum of the forces in the y direction. For the sum of the forces in the x direction, we'll call that equation 2. And for the sum of the moments, we'll call that equation 3. I'm going to take equation 2 and equation 3 and put them together. If I look at equation 3, I can cross out an r on this side of the equation and an r on that side of the equation. And I can write this as 2 times the maximum value for the force of static friction is equal to mr alpha. This equation 2 is equal to mr alpha, so I can say 2 times the maximum value for the force of static friction is equal to p cosine theta minus the force of static friction max. And then bringing this over to the other side, I get 3 times the maximum value for the force of static friction is equal to p cosine theta. But because I'm at the maximum value for the force of static friction, I can use the equation for the maximum value for the force of static friction, which says the maximum value for the force of static friction is equal to the coefficient of static friction times the normal force. So this is the definition of the maximum value for the force of static friction. Then I can take equation 1 and use it here and say the maximum value for the force of static friction is equal to the coefficient of static friction times the normal force, which is p sine theta plus mg. And I can take that and put it in for my maximum value of the force of static friction, and I get 3 times mu s times p sine theta plus mg is equal to p cosine theta. And now I want to solve this for p. So I can distribute the 3 times the coefficient of static friction and then pull the term with the p sine theta over to the other side. So I get 3 mu s mg is equal to p cosine theta minus 3 mu s p sine theta. Then pull out the p and divide by what's left. So you get p is equal to 3 mu s mg divided by cosine theta minus 3 mu s sine theta. Okay, so now in order to find the maximum value for p that they asked me for, I just have to take the values that they give me and plug them in to my symbolic expression here. And so I have p is equal to 3, the coefficient is 0.25, mg is equal to 50 pounds, my theta is equal to 30 degrees, so this is cosine of 30 degrees minus 3 times 0.25 times sine of 30 degrees, and this gives you 76.37 pounds for the maximum value at which you can push and still have rolling without slipping. They also asked you to find the angular acceleration. You can go back and in order to find the maximum, or in order to find the angular acceleration, you can use equation 1 to find the maximum value for the force of static friction, and then once you know that, you can either use equation 2 or equation 3. I'm going to let you do that on your own. And instead, we're going to look at our symbolic expression for p. And let's first see what would happen here if theta is equal to 0 degrees, what do we get for P? So if theta is equal to 0 degrees, cosine of 0 is 1, sine of 0 is 0. So for the maximum force with which we could push and have rolling without slipping, we would have 3 times the coefficient of static friction times mg. So if your coefficient of static friction is 0, at 0 degrees, there's no way that you can push and have rolling without slipping. Okay, and next we're going to look at when cosine theta is equal to 3 times the coefficient of static friction times sine theta. That means our denominator is equal to 0. If our denominator is equal to 0, then for P max, you get infinity, which means you can push as hard as you want, and you're still not going to have any slipping. If the coefficient of static friction is equal to 0 here, so if mu s is equal to 0, that means cosine of your angle is equal to 0, which means theta is equal to 90 degrees. So if there's no friction, it makes sense that you can push straight down like this at an angle of 90 degrees, and you're not going to have any slipping. Of course, in this case, your cylinder is not going to go anywhere, so you're really not going to have any rolling either, but you can push down as hard as you want and your cylinder will not slip. And if you want to know if the coefficient of static friction is not 0, what angle you can push at, you can say tangent theta, you'd get by dividing both sides by cosine, then bring the 3 mu s over to the other side, like this, and you get theta is equal to the inverse tangent of 1 over 3 mu s. And at that angle, you can push as hard as you want, and you will not have any slipping.